Dear students, hope you are doing well. Today we will discuss the difference between the atomic spectroscopy and molecular spectroscopy with the highlights of Born-Oppenheimer approximation. After studying this module, you shall be able to understand what is atomic spectroscopy, how atomic spectroscopy differ with molecular spectroscopy, and then finally Born-Oppenheimer approximation and its significance. Now you know every chemical element has a unique number of electrons at their ground state. Thereby, an atom will absorb or release energy in a pattern unique to its elemental identity. The light from atomic process is seen to consist of collections of very narrow discrete lines at wavelength characteristics of the atoms involved when dispersed with a prism or grating. The discrete spectrum is a signature of quantization in atomic systems. Simple Bohr model can nicely explain line spectra and quantized energy level in hydrogen. Additional effects like screening of nucleus by inertial electrons, the interaction of the electron spin with internal atomic consideration, and most importantly, selection rules for allowed transitions must be considered for more complicated atoms than hydrogen. For example, when a suitable source of energy is passed through a medium of sodium atoms, excitation of the 3s electron to the 3p state takes place, and sodium spectrum is dominated by bright doublet known as the sodium D lines at 588.99 and 589.59 nanometers. The line at 589 has twice the intensity of the line at 589.6 nanometer. On the other hand, when atoms combine into two molecules due to vibrational and rotational normal modes of structures, additional energy terms arises. Now, due to transition between these states, a complex band spectroscopy arises which allows study of the interatomic potential and the elucidation of the chemical bond. Both the atomic and molecular spectra are found to be in the complete accord with the Schrödinger theory, and a deep understanding of atomic structure and molecular structure is possible. Now, I will explain little bit about atomic spectra. Now, quantum numbers are very important to understand the energy, size, shape, direction and angular momentum of an orbital. For example, principal quantum number n governs the energy and size of the orbital. Azimuthal quantum number L governs the shape of the orbital and electronic angular momentum. Now, the magnetic quantum number m governs the direction of orbital and the electron's behavior in a magnetic field. But spin quantum number S governs the axial angular momentum of the electron. Now, the energy of each orbital changes significantly from atom to atom. There are two main contributions to this energy. Number one, attraction between nucleus and electrons, and repulsion between electrons in the same atom. Having only one electron, let us say hydrogen, can be considered as simplest example. Also, here the second factor, that is repulsion between electrons in the same atom, is completely absent. Now, the energy levels of electrons of an atom are known as terms. For a single electron atom like hydrogen, the energy level corresponding to L is equal to 0, 1, 2, 3, 4, etc. are known as S, P, D, F, G, etc. respectively. Now, due to the absence of interelectronic effects, all orbitals with the same n value have the same energy in hydrogen. This means that 2s and 2p orbitals are degenerate. Same is true for 3s, 3p and 3d orbitals. Now, obviously, 2s, 3s and 4s orbitals differ significantly in terms of energy because their principal quantum number are different. Now, solving Schrödinger equation for s orbital, energy can be written as epsilon n is equal to minus m e to the power 4 divided by 8 h cube c epsilon 0 square n square is equal to minus r by n square centimeter inverse, where n is equal to 1, 2, 3, 4. Here E0 is the vacuum permittivity and other fundamental constants E, m, c and h have been collected to give a constant r, which is known as Rydberg constant. As the p d orbitals have the same energy as the s, so equation 1 can represent all the electronic energy levels of hydrogen atom. Now, the lowest value of energy n is equal to minus r centimeter inverse when n is equal to 1, representing most stable or ground state. With increase of n, that is the principal quantum number, like n increases to infinity, reaching a limit of 0 at n is equal to infinity. And this represent ionization or complete removal of the electron. Importantly, 0 energy corresponds to infinite separation of the electron from the nucleus. As there is an attraction between the negative electron and the positively charged nucleus, the closer the electron comes to the nucleus, the energy becomes more negative, and the energy becomes 0 if the electron is separated from the nucleus by an infinite distance. Now, the energy levels for n is equal to 1 to 4 and L is equal to 0, 1, 2 are shown in the figure shown in the screen. All the p and d states for each n are degenerate. So, the selection rule is delta n is equal to anything and delta L is equal to plus minus 1 only. Now, considering the selection rules, an electron in the ground state, that is in 1s, can undergo a transition into any p state, that means 1s to np, where n greater than is equal to 2, and a 2p electron can have a transitions either into an s state or a d state. So, it can happen like 2p to ns or 2p to nd. Now, as s and d orbitals have the same energy, that is degenerate, the energy of both these transitions will be same. Now, if an electron in a lower state n double prime can undergo a transition into a higher state n prime, energy of absorption will be delta E is equal to E n prime minus E n double prime centimeter inverse. Now, if we put in the wave number, that is nu bar is equal to minus r by n prime square minus second bracket minus r by n double prime square centimeter inverse. So, we can write r into 1 by n double prime square minus 1 by n prime square centimeter inverse. Now, if the electron falls from n prime to state n double prime state, spectral line will be produced due to the emission and L must change unity. Now, taking absorption into consideration, let us consider a transition, let us say from 1s to n prime p, where n prime is equal to 2, 3, 4. Now, for this we can write nu bar Lyman is equal to r into 1 by 1 minus 1 by n prime square is equal to r minus r by n prime square centimeter inverse, which will be equal to 3 r by 4, 8 r by 9, 15 r by 16, 24 r by 25 centimeter inverse for n prime is equal to 2, 3, 4, 5 etc. This series observed in the atomic hydrogen is very famously known as Lyman series after its discoverer. Now, the appearance of this spectrum is shown in figure 2 and shown in the screen. It can be seen that the spectrum converges to the point r centimeter inverse and very precise value of r 109677.58 centimeter inverse can be obtained. At n prime is equal to infinity, ionization, that its complete removal of electron occurs and the energy required for that may be calculated as 2.178 into 10 to the minus 18 joule or 13.595 electron volt. Now, another set of transition can occur from an electron initially in the 2s or 2p states, and corresponding series is called Balmer series after its discoverer. Now, here transition occurs from 2s to n prime p or 2p to n prime s or n prime d. So, the frequency or wave number will be nu bar Balmer will be equal to r into 1 by 4 minus 1 by n prime square. centimeter inverse, which will be equal to 5 r by 36, 3 r by 16, 21 r by 100 centimeter inverse for n prime is equal to 3, 4, 5. Similarly, other series like Paschen, Brackett, Pfand are observed for n double prime is equal to 3, 4, 5, and these spectra were observed long before the modern theory of atomic structure was developed. Rydberg empirically correlated this series and calculated the wave numbers for the spectral lines. It is worthwhile to mention that each line series shows a continuous absorption or emission to high wave numbers of the convergence limit, which represents the situation where the electron has absorbed sufficient energy from radiation to escape from the nucleus with zero velocity. It is also important to note that it can even absorb more energy and can escape with higher velocities. As the kinetic energy of an electron moving in free space is not quantized, any energy above the ionization energy can be absorbed. Hence, the spectrum in this region is continuous. Now, I will explain the difference between atomic and molecular spectra. Already in one of my earlier class, I described about molecular spectra. The molecular spectroscopy may be defined as a study of the interaction of electromagnetic radiation and matter. The molecules in the sample can absorb some wavelengths that can be passing through the sample and can move to a higher energy state from the existing lower energy state. Now, the sample will absorb particular wavelengths, but not all, depending on the chemical composition of the sample. Then, depending on the absorbed wavelengths and the intensity of absorption, the nature of the energetic transitions that a molecule is able to undergo or able to showcase can be understood. Then, by understanding the transition and based on the information gathered, structure of the molecule can be elucidated. For example, nucleus and electrons are tiny charged particles and their spin can be associated with a magnetic dipole. Now, the reversal of the dipole followed by spin reversal and interaction with the magnetic field of the electromagnetic radiation at appropriate frequency can result in NMR or ESR spectroscopy. Now, by employing NMR or ESR spectroscopy, we can understand structure, conformations of organic inorganic molecules. Similarly, the molecules which have a permanent dipole moment like H2O is microwave active and can show rotational spectra. When H2O molecule is rotated, it can be seen that plus and minus charges change places periodically and the component of dipole moment fluctuates regularly. Now, when interaction occurs, energy can be absorbed or emitted in the form of rotational spectrum. Now, the best example in day-to-day life is the use of microwave oven in our kitchen. Normally, in conventional cooking, first peripheral part of the food material is cooked, heated and then inside is cooked. But cooking using microwave oven is different. Here, water molecules which have permanent dipole moment are normally stay in plenty amount in food material and can rotate contrary to the large size biological molecules. Now, the excess rotational energy of the water molecule is re-emitted as heat and the food materials are cooked from inside. Likewise, vibrational spectroscopy like FTIR, electronic spectroscopy like UV visible is very important spectroscopic tools for chemists to understand the structure of the molecules. In addition, some other spectroscopic technique like using X-ray as a source or Mossbauer spectroscopy, Raman spectroscopy named after their discoverer are very much useful to understand the structure of materials and molecules. Now, I will explain the difference between atomic and molecular spectra. Now, the key difference between atomic spectroscopy and molecular spectroscopy is that the atomic spectroscopy refers to the study of the electromagnetic radiation absorbed and emitted by atoms, whereas the molecular spectroscopy refers to the study of the electromagnetic radiation absorbed and emitted by molecules. Therefore, Atomic spectroscopy determines the type of atoms present in a given sample, while molecular spectroscopy determines the structure of molecules present in a given sample. Very narrow discrete lines at wavelength characteristics of the atoms involved are the signature of quantization in atomic systems and atomic spectroscopy. However, band spectroscopy, which allows study of the interatomic potential and the elucidation of the chemical bond, are the signature of molecular spectroscopy. Now I will explain one very important approximation for the spectroscopy as well as quantum mechanics, which is called the Born-Oppenheimer approximation. Now you already know that atomic spectra arise from the transition of an electron between the atomic energy level, whereas molecular spectra came from the molecular rotation, molecular vibration and electronic transition. Now according to Born-Oppenheimer approximation, the total energy of a molecule is given by E is equal to E transitional plus E rotational plus E vibrational plus E electronic. Now according to this equation, total energy of a molecule is the sum of transitional, rotational, vibrational and electronic energy. Now all of these energies except transitional energy are quantized. Also the transitional energy is negligibly small and transitional motion is dissipated as heat. Thereby it is not involved in molecular spectra. We have to remember it. Now likewise, nuclear spin energy is very small and can be omitted too. Now the Born-Oppenheimer approximation can be represented as E total is equal to E rotational plus E vibrational plus E electronic. Now this equation implies that the electronic, vibrational and rotational energies of a molecule are completely independent of each other. It can be seen later to what extent this approximation is invalid. Thereby a change in the total energy of a molecule can be written as delta E total is equal to delta E rotational plus delta E vibrational plus delta E electronic joule, or delta E epsilon is equal to delta E rotational plus delta E vibrational plus delta E electronic centimeter inverse. Here it must be noted that the approximate orders of magnitude of these transitions are delta E electronic equivalent to delta E vibrational into 10 to the power 3 equivalent to delta E rotational into 10 to the power 6. Now it is clear that vibrational changes may generate a quark structure and the rotational changes fine structure on the spectra of electronic transitions. It is also known that pure rotational spectra are shown by molecules possessing a permanent dipole moment, and vibrational spectra need a change of dipole during the rotation. However, electronic spectra are given by all molecules, since changes in the electronic distribution in a molecule are always accompanied by a dipole change. This means that any homonuclear molecule like H2 or N2 which show no rotation or vibration rotation spectra can generate an electronic spectrum and show vibrational and rotational structure in their spectra, from which rotational constant and bond vibration frequencies can be derived. This is very important. So it is also interesting to note the Schrodinger equation for a hydrogen atom can be solved precisely, but it is very difficult to solve the problem of a molecule exactly, because the simplest molecule at least consists 2 nuclei and 1 electron, that is 3 particles. So to calculate the electronic energy, we need to solve the electronic Schrodinger equation. The complete Schrodinger equation covers both the nuclear and electronic motions. Now in order to separate the part of Schrodinger equation due to electronic motion, Born and Oppenheimer assumed that since the nuclei are several thousand times heavier than electron, the nuclei may be assumed to be stationary when the electrons move. So the electronic wave functions can be obtained by solving the electronic equation for some fixed position of nuclei. Alternatively, it can be said that nuclei move relatively slowly and may be treated as stationary while the electrons move relative to them. Now wave function of the electron alone can be solved using Schrodinger equation and by applying Born-Oppenheimer approximation, which has been found quite satisfactory for ground state molecules. For example, calculation shows that the nuclei of hydrogen molecule move through only about 1 picometer, However, electron speeds through thousands picometer. So, you can say that nuclei is stable or stationary compared to electron. Thereby, the error of assuming that nuclear stationary is very small. Now, I can summarize my today's lecture. In this module, you have learned that atomic spectroscopy refers to the study of the electromagnetic radiation absorbed and emitted by atoms. Since chemical elements have unique spectra, we can use this technique to analyze the composition of elements in a sample. Now, molecular spectroscopy may be defined as a study of the interaction of electromagnetic radiation and matter. Differences between atomic and molecular spectra are highlighted. Now, we found that from atomic spectra, discrete lines at wavelength characteristics of the atoms involved. However, from molecular spectra, a complex band spectroscopy arises, which allows study of the interatomic potential and the elucidation of the chemical bond. Different series like Lyman, Balmer, Paschen and selection rules for the transition is explained. Most importantly, we have highlighted the Born-Oppenheimer approximation for molecular spectroscopy, and thank you very much for your kind attention.